Okay, so this is going to be the last part of our lecture series, and we're going to be talking about Poisson brackets. So we motivated the idea of Poisson bracket in the last lecture, but now we're going to have a little look more what we can do with it. So if you recall, we defined a Poisson bracket of A and C to be the sum over I of the partial derivative of A with respect to Q sub I times the partial of C with respect to P sub I minus the partial of A with respect to Q sub I or P sub I times the partial of C with respect to Q sub I. Right, so this is how we defined it, and this is for some functions A of Q and P, B of Q and P, and C of Q and P. Right, so what we're going to go through now is just some of the properties of Poisson brackets, and then we're going to ditch the definition completely and see what we can do with it. So the first property we're going to look at is that if you take the Poisson bracket of A and C, this is the same as saying the negative Poisson bracket of C and A. This is called skew symmetry or anti-symmetry. And you should be able to see that from our definition, that if you were to replace these functions with, or if you were to swap these around, it would be the same as just putting a negative in front of the original Poisson bracket. Okay, so the next one we're going to have a look at is that if you take the Poisson bracket of some function, A with itself, will give you 0. And this is simply because if you have the derivative of A with respect to a variable times the derivative of A with respect to another variable minus the same thing, we're just going to, they're going to cancel each other out and get 0. Next up, we're going to have a look at linearity. So we're going to show that Poisson bracket is a linear function. And for that, we're going to need to show two things. We're going to see that the Poisson bracket of some k times A and C is the same as the Poisson bracket of A with some k times C, which is the same as saying k times some A and C. And this is for some k that is constant. And you can see that this occurs by just taking a constant out of the derivative, which we know from basic differentiation rules will work out. And so the final thing we're going to have a look at is that the Poisson bracket of A plus B with C is the same thing as saying the Poisson bracket of A with C plus the Poisson bracket of B with C. And these two together will give us linearity. Okay, so now that we have our few properties, we're going to have a look at taking some Poisson brackets of specific objects. And what we're going to use is if we take the Poisson bracket of Q sub I with some Q sub j, this is the same as the Poisson bracket of P sub I with P sub j, which is 0, where A and J are just some different indices. And then the next one we're going to have a look at is the Poisson bracket of q sub I with p sub j, and this returns something called the Kronecker delta of I and j. And basically what the Kronecker delta symbol means, so it's denoted like this. So this is the Kronecker delta. And what this means is this is going to be equal to 1 for I equals j, and it will equal 0 for all I not equal to j. So this will basically tell you that if we have q sub 1 Poisson bracket with p sub 1, it will give us 1. But if we have q sub 1 Poisson bracket with p sub 2, it will give us 0 back. This Kronecker delta is a very important idea in physics, and we use it a lot, especially in like quantum mechanics. But that's really all we'll need it for when it comes to classical mechanics. Okay, so now that we have a pretty good toolbox made up, we are going to have a look at what we can do while ditching the definition entirely. So let's have a look and try compute, just with these rules, the Poisson bracket of some q to the n times p. Right, so what I'm going to do is I'm going to give you the answer to this, and we're going to work through it and prove it inductively. So this will give q, or n, times q to the n minus 1. Right, so yeah, this will give n times q to the n minus 1, and we're going to prove it inductively. And the way that this works is just boarding off our toolbox here. So the way induction works, that if you might have realized before, or might have come across before, is that we assume it true to be the general case n. We prove it to be true for the case of n plus 1, and then we show that it's true for some earlier version, some base case, usually n equals 0 or n equals 1. We'll use n equals 1 in this case. So we assume this to be true, and then if we work out the Poisson bracket of q to the n plus 1 with p, we'll get that that's the same as saying some q times q to the n plus, or q to the n with p. And this is actually one thing that we haven't put in our toolbox yet, is the idea of multiplying these two together. So what we'll have in this case is, if we remember our product rule, we'll have that if we have the Poisson bracket of a times b with c, this is the same thing as saying a times the Poisson bracket of b with c plus b times the Poisson bracket of a with c. So it's like the product rule. And using this, we can say that this is q times the Poisson bracket of q to the n with p plus q to the n times the Poisson bracket of q with p. But we'll know from our use of the Kronecker delta here that this will go to 1. And so we'll have that this is equal to q times the Poisson bracket of q to the n with p plus q to the n. Okay, and now that we have this association shown with our toolbox here, let's now use our hypothesis up here and show that we get the same thing. So let's just box this. Right, so in if we're going to be taking our hypothesis to be true, we'll get q to the n plus 1 and p is equal to n plus 1 times q to the n. Okay, so now we expand this here blue box, and we'll get that this is there, or this purple box rather. We'll expand this Poisson bracket here out, and we'll get q times, assuming this to be true, n times q to the n minus 1 plus q to the n. This q will cancel with this q to the minus 1, and we'll get n times q to the n plus q to the n, which is in fact the same thing that we found by plugging n plus 1 into this. Okay, so now that we've shown that assuming this is true for q to the n, we can prove that it's true for q to the n plus 1. Let's start off with using the base case, so n equals 1, and see if it's true for there. And if it's true for there, then it will hold for all positive integer n's. So we then just need to show that the Poisson bracket of q to the 1, so this is just q, and p is equal to 1, which is our n, times q to the 0, which is just 1, which in fact is what we showed back here with our Kronecker delta, that if q sub I and p sub j, if I and j were equal, we'd get into 1. And so we've proven that by induction, the Poisson bracket of q to the n and p is equal to the derivative with respect to q of q to the n. And this will hold true for anything going into that first plot here, that if you take the Poisson bracket of some function f with p, we'll get that the derivative of f with respect to q, and then if we were to take the Poisson bracket of some function f with and q, we'd get negative derivative with respect to p. Okay, so our next topic is going to be angular momentum. We worked a little bit with angular momentum before, but not too much. So what we're going to be doing now is we're going to remember that when we were talking about it originally, we said that the change in the x coordinate was equal to y times some infinitesimally small delta, and infinitesimally small change in the y coordinate will be equal to minus x times delta. And we also found out that if we had some quantity q, given the Lagrangian was invariant, we would have that the p sub x times some function of x plus p sub y times some function of y would also be invariant. And we'll call this new quantity the angular momentum, and we'll denote it with the letter L, not to be confused with the Lagrangian L. So we'll have L, and using a change of sign, we'll have x p sub y minus y p sub x. And this is how we'll denote our angular momentum. Now in 3D space, angular momentum is a vector, and our rotation formulae take on a new type of meaning. They become a way of rotating a system about an axis. So in this case, we are actually taking the z component of the angular momentum, and there's different ways of doing this, or different ways of showing this, which we'll go through now. But when we talked originally about vectors and two ways of multiplying, this is our other way. This is called we use the cross product in this case. So very quickly, we can say that the vector L is equal to the position vector X, or the position vector or, cross with the momentum vector. And what this basically means is that the momentum, or the angular momentum vector, will be perpendicular to the position vector and the momentum vector. So that's what a cross product does in a 3D graphical sense, is that it takes two vectors as an input and will shoot out a third vector that is perpendicular to both of the original vectors. Okay, so by cycling through the different coordinates, we find that that L sub z, which we had here, was equal to x times p sub y minus y times p sub x. L sub x is equal to y times p sub z minus z times p sub y. And Ly is equal to z times p sub x minus x times p sub y, or p sub z rather. Okay, so now that we have our different Lz, Lx, and Ly, let's have a look about taking Poisson brackets with them. So as one might expect, that if you were to be completely invariant under rotational symmetry, all of these will all be invariant as well. Right, so if the angular momentum was to be conserved, rather, all of these would be invariant. So if we had, say, x, we're going to take the Poisson bracket of x with L sub z, the Poisson bracket of y with L sub z, and the Poisson bracket of z with L sub z. So for x, we'll get that this is just going to be, this is just going to be minus y. If we take it with y, we'll just get this is going to be x. And if we take it with z, we'll just get this to be 0. So what we've in essence done is, using our Poisson brackets, we've gotten back to our delta way of rotating things about an axis. So we couldn't therefore say that the Poisson bracket of x with L sub z was approximately equal to delta x. The Poisson bracket of y with L sub z is approximately equal to delta y. And the Poisson bracket with z with L sub z was equal to delta z, which is equal to 0. So this is what we mean when we say we were able to now use our Poisson brackets to rotate something about an axis, given that we're taking the angular momentum of that specific axis in the second part of our Poisson bracket. And we'll kind of look a little bit more now at another mathematical symbol similar to the Kronecker delta, called the Levi-Civita symbol, that will help us expand this a little bit more. Okay, so we're going to have a look at the Levi-Civita symbol before we carry on a little bit more about angular momentum. So the Levi-Civita symbol is denoted by an epsilon and then an I, J, K at the bottom. And it's similar to the Kronecker delta, because if you remember, we had the Kronecker delta, which was delta of I and J, which would equal is 1 for I equals J, and would equal 0 for I not equal to J. Now the Levi-Civita symbol is a little bit more complicated, a little bit more nuanced than that, because it uses three variables, or three indices rather. But we can right at the back say that it will be equal to 0 if I equals j, or if I equals j, j equals k, or I equals k. So if any two symbols are the same, or if any two indices are the same, it's 0, which is easy enough. This is where we introduce a little bit of the nuance, and basically the way that we want to introduce this is if we make a, let's say we use 1, 2, and 3 as our indices. So we'll have epsilon of 1, 2, and 3. Basically, we want to put these on almost like a clock, like a circle. So we'll have 1, 2, 3. So in a circle, like we're going clockwise. If the symbols are going 1, 2, and 3, like in this case, we'll get a 1, which is the same as if it was 2, 3, and 1. So, which is the same as saying epsilon 2, 3, and 1, which is also the same as saying epsilon of 3, 1, and 2. So if our I, then j, then k go around in a circle clockwise like this, so we'll go I, then j, then k, or I, then j, then k, or I, then j, then k, we'll get 1 out of it. However, if we reverse that motion and we go I, then j, then k in the counterclockwise fashion, we'll get -1. So this is the same as of epsilon of 1, 3, and 2, which is the same as epsilon of 3, 2, and 1, which is the same as epsilon of 2, 1, and 3. Right, and that's basically it. That's all there is to the Levi-Civita symbol. It's just a nice notational trick that we're going to be using a little bit in our angular momentum. Okay, so now that we have our Levi-Civita symbol, we can use this to try and help us with our angular momentum. And basically the key to doing this is if we have our epsilon of I and j and k, and we have our circle, 1, 2, and 3, we just need to think about what each coordinate will be. Will x be 1, 2, or 3, and so on. And we find this that x is going to be 1, y is going to be 2, and z is going to be 3. So this just helps when we're doing our rotations. That's how it'll work out. So when we have, say, for instance, if we want to take the Poisson bracket of some x to the I with some L sub j, we'll get that this is the sum of x sub, of epsilon sub I, j, k times p of k times some x of k. Okay, I also meant to say this is being summed over k. Right, so now we can also use this to help us with momentum as well. So we could take the Poisson bracket of some p sub I with some L sub j, and we will equally find this to be the sum over k of epsilon of ijk times p sub k. Okay, so if we were to have a look at these two, we see that if we put a component of x in with a component of L, we'll get spat out a certain rotation of like what we had originally with our angular momentum or when we did a few minutes ago. And then the same thing happened if we put in our components of momentum. And this is a curious kind of connection. And what it leads us to believe is that if you have any function, we'll say any function f, we took a Poisson bracket going across on a certain axis, and we took the Poisson bracket with L, we'd get the rotation of that function. So this is a really big idea that we can say that the angular momentum then is the generator of rotations. So it acts on, or it can act on other functions when given the chance by putting in a Poisson bracket, and it'll show us how that function will rotate. Okay, so now you might be asking what happens when we take the Poisson bracket of two different components of angular momentum. And in this case, what we'll get is we have the Poisson bracket of L sub I with L sub j. We will yet again get the sum over k of epsilon of ijk times L sub k. So we can see that that angular momentum is still a generator of rotations, even with other components of angular momentum. And so we can think of using this in a number of ways. And an example that we're going to go through is if we imagine we have a spinning ball in the depths of space where no other influences are acting upon it, and then we imagine there's some charge with this ball that is. So the ball is now moving with, or is now operating in a magnetic field. And so we won't really need to know too much about the electromagnetism to deal with this, but I can tell you that the energy created by this ball spinning is proportional to the magnitudes of the angular momentum, so how fast or how heavy the ball is, etc., and the strength of the electric or the magnetic field, times the cosine of the angle between the two vectors. And this should be kind of ringing alarm bells as to something that we covered a lot earlier on, which was the dot product, right? So we said that if we had the dot product of u and v, this was the magnitude of u times the magnitude of v times the cosine of the angle between them. So we can now say that in this case, we have the Hamiltonian, so the total energy of the system is proportional to the angular momentum dotted with the magnetic field. Magnetic field is also given as a vector. So we can group these all together, and we won't really worry. We can group a lot of the terms up together as a constant. So like the magnitude of the magnetic field, etc., and the cosine and cos theta, and we'll group that as a constant called omega. And we'll say that the the ball is spinning such that the angular momentum going along the axis is along the along the z-axis. So we'll say that then h is equal to some omega, which carries all the constants, times L sub z. Right. So if there were no magnetic field, the rotational symmetry would be obvious. However, we thought that there is now something to rotate relative to. This rotational symmetry kind of gets ruined. Okay, so we'll have a look now and try guess how this system will unfold. So if we had no magnetic field, we'd have rotational symmetry completely, but our magnetic field gives us something to rotate relative to, and so ruins that. And so ultimately, the axis of rotation will eventually move. And how this works, you can hazard a guess, but the way that it'll end up working is it'll precess, so kind of like around the magnetic field. So the way that we can show this is by taking time derivatives and seeing how the angular momentum vector will change with time. So if we wanted to find the change of time of, let's say, L sub x, and L sub y and L sub z, we just need to take the time derivatives of those, which we'll remember we can use Poisson brackets for. We can say that this is the same thing as the Poisson bracket of L sub x with the Hamiltonian h. Likewise for our other two. Okay, and so we'll see that just quickly off the bat that we can sub in our h here, our Hamiltonian, which is omega times Lz, and omega being a constant, we can come out front. And so we'll have these as equal to omega times L sub x with L sub z, which is equal to omega times L sub y and L sub z, which is equal to omega times L sub z with L sub z. And very quickly, we can know that L sub z will go to 0 because the Poisson bracket of two identical functions will immediately go to 0. And for the other two, we only need to look at what we were talking about earlier, while this would be to do with the Levi-Civita symbol. So in this case, we get that L sub x with L sub z will give minus L sub z, minus L sub y, and so we'll get this as minus omega L sub y. Similarly, L sub y will go to positive L sub x, and so we'll get omega L sub x. And this here, these two here, will tell us how our angular momentum will move. And we'll notice that having this L sub x dot equals minus omega L sub y, and L sub y dot equals omega L sub x. Well, that looks very similar to what we had before, where we had the change in x equals minus y times some delta, and the change in y is equal to x times some small change delta. And so when we derived these, they were for rotations. And so we've shown therefore that as the angular momentum will move on, so that as it will change with respect to time, that these will move in a circle. Okay, and that circle will be about the L sub z axis, which is the axis of rotation. Okay, so finally we're going to have a small look at symmetries and conservation laws again. So we had a look before and we were able to say that the change in some function f under rotation would be the Poisson bracket of that function f with the angular momentum of the direction it was rotating about. And let's consider a couple more examples of this. So if we remember that we could write for some function f, we can have df dx as the Poisson bracket of f, which is a function of x, and p. And this basically says that under a small transformation f, so the change in f rather, would be the same as some small delta, or we'll denote this epsilon. So some epsilon where epsilon is a small number times df dx, right? So the change, so how much f responds to change with x times some distance in the x direction. And we can say this equally so as epsilon, some number, times Poisson bracket of f with p. Right, so this kind of gives us a connection between momentum and spatial translations, which, as we've seen before, is how we've been able to derive the conservation of energy as invariance under time translation, under spatial translation. Finally, we had a look at what we'll have a look at how the Hamiltonian will change. Okay, so another example of that would be with time translation invariance, leading to energy conservation. So we were able to use this with our Hamiltonian H. But let's try generalize it with any transformation generator we'll call G, which is a function of the phase space Q and P. So now we'll we'll say that the change in some Q is equal to the Poisson bracket of this Q sub I with G, and likewise the change in some P is equal to the Poisson bracket of P sub I with G. And this, which generates therefore infinitesimal transformations in the phase space. And this general transformation may or may not be a symmetry, but how we would find if it is a symmetry in this case is if the change in the Hamiltonian, so if delta H will be equal to 0. So we can write these symmetries therefore as to just go into perspective, we see that the change in a quantity here is equal to the quantity Poisson brackets with the generator. So then we can say that the change in the Hamiltonian is the Poisson bracket of the Hamiltonian with the generator, which we said must be equal to 0. And so what this does is it tells us that this one Poisson bracket will tell us how H changes under G, and will tell us how G changes with time. And so if the energy is conserved, this will equal 0. So this has been quite a long lecture series talking about different areas of mechanics, and I really implore you to go and research a little bit more, because a lot of this has been very superficial, and there's a lot more you can do with Lagrangian mechanics, so much more you can do with symmetries. If you're very interested in this idea of symmetries and the combination of conservation laws and global symmetries, I'd say have a research into something called Noether's theorem. And yeah,